questions? So I think last time we started chapter 2. I think I signed like up through 24, 25, something like that. Does anybody have any questions? Does anybody have anything on 1 through 24 or whatever that you want to talk about, or 25, whatever it was? I don't remember exactly. No? Okie dokie. Well, we can always ask next time. That's fine. Today, we're going to start by talking about section 2.2. Okay. Let's start here by talking about trig functions of acute angles. So recall in geometry, when we did sine of x, cosine of x, tangent of x, where did we have to get the x from? Okay, it had to be an angle measure, specifically from where? An angle. Okay, what kind of triangle? And what kind of angle measure from that right triangle? Acute, right? You couldn't use the 90-degree angle. Right? So back in geometry, when we did sine, cosine, and tangent of something, that something had to be an acute angle from a right triangle. Okay. So let's say we have our right triangle here. Now I'm going to label this angle as theta. So that symbol is just the Greek letter theta. The convention often is in trigonometry that we'll use the Greek letters for angle measures. So that Greek letter is the theta. If you're ever curious what a symbol is that I draw and you're not sure what it is, holler at me and I'll talk about it in more detail. So relative to this angle theta, what do we call this side here? Adjacent, right? Heard somebody whisper it. And what do we call the green side? Opposite. Great. And then the blue side we call hypotenuse. So we use those names, opposite, adjacent, and hypotenuse, along with the acronym SOHCAHTOA to help remember our definitions for sine, cosine, and tangent, right? So we say that sine theta is opposite over hypotenuse. we say that cosine theta is adjacent over hypotenuse and we say that tangent theta is opposite over adjacent. Everybody remember all this? Now, if I look at that triangle, I have I have 3 different side lengths, right? If I want to make a ratio out of that, there's 6 possible ratios I could make, right? Like, why not have hypotenuse over opposite? Or hypotenuse over adjacent, or adjacent over opposite, right? Like, why not have those things? Anybody have a reason why not? Good. It's just because we didn't tell you about them. There are trig functions named for those ratios. Let's tell you about them right now. The first one we call cosecant. And that is hypotenuse over opposite. The next one we call secant. Which is hypotenuse over adjacent. And the last one we call cotangent. Which is adjacent over opposite. And you're probably now thinking, oh, brother, Mr. Kulik, is that like 3 more things that I have to memorize? Yeah, it is, but it's not so bad. Let me explain. Did you notice a relationship between sine and cosecant? They're reciprocals. Yep, exactly. How about between cosine and secant? Reciprocals. And tangent and cotangent? Just reciprocals, right? So, if I remember SOHCAHTOA, which I already knew, all I need to remember is which reciprocal pairs together, right? Everybody's okay with that? And if I remember which ones pair together and SOHCAHTOA, then I know the 3 new definitions that I've given here. Everybody's cool with that? That's going to be the easiest way to remember it. So, is anybody going to have a problem remembering that tangent and cotangent go together as a reciprocal pair since they both have the word tangent in them? Everybody should be cool with that, right? Good with that? So now all I have to do is keep straight secant and cosecant, which one goes to which, right? Here's the way that Mr. Kulik remembers it, is that no cos go together. So cosine does not go with cosecant. It goes with secant. And as a result, the only one left then is sine that has to go with cosecant. Is that okay with you guys? If you think about it that way, there's kind of almost nothing left to remember, very little less to memorize, which is what Mr. Kulik would like. I don't want to spend my time memorizing things. I want to spend my time doing mathematics. Right? You guys are so excited today. I love it.
It's Monday.
It is Monday. It's very Monday. Well, let's do some examples. Yes, of course. So let's say I ask you guys to find the 6 trig ratios for theta, and I give you this triangle. What's the first thing you should notice right away? It's a right triangle, great. Did you notice anything odd about this right triangle?
Theta. Is it theta?
That's theta. That's the name for that.
Has a theta symbol in it.
Yeah, but that's okay because I'm asking you to find the 6 trig ratios for theta. So I was expecting to have a theta in my picture. Do I know all the side lengths for the right triangle? No, I'm missing one, right? Am I going to need that to write all my trig ratios? Yeah, so I'm going to have to find that first. How do I go about finding a side length of a right triangle if I know the other 2 sides? The Pythagorean theorem. Great. What is the Pythagorean theorem again? That's correct. So that's the formula for the Pythagorean theorem. What do I have to be careful about when I'm plugging my numbers into the Pythagorean theorem, though? Can I just plug them in wherever I want? No. Matt?
Well, for the first 2, A and B, it can be either 2 or 5, but the C has to be the hypotenuse.
Yeah, very good. So the big thing I have to remember is the hypotenuse has to be my C. Now that is what I'm looking for in this picture, right? So that's fine. And as Matt said, we can plug in 2 or 5 into either place. It doesn't matter. So now I just kind of grind through some algebra. And I get that hypotenuse is the square root of 29. Everybody feel okay to hear? That's not a big deal. All right, now I just need to do my 6 trig ratios. So sine theta. How do I find sine theta? SOHCAHTOA says, what's the ratio? Opposite over hypotenuse. Very good. What's the opposite in this case? It's not 2. It's 5. So remember that opposite is always relative to the angle. So 5 would be the opposite in this case. And the hypotenuse is? Square root of 29. Great. Now, do we like the way that this final answer looks? No. What's wrong with it? Yeah, there's a square root in the denominator. How can I fix that? Can I just erase it? No, Mr. Kulik. You silly goose. What do we do to fix that? Do you remember? What's that? Yeah, we're going to multiply the top and bottom by the conjugate when our radical is just a square root. It's just multiplying the top and bottom by whatever that square root is. Now, what's the square root of 29 times the square root of 29? Quick in your head. $29, right? Well, how does that work, Mr. Kulik? Square root of 29 times square root of 29 is square root of 29 squared. And then the squared and square root just cancel each other out, right? That's why I said, like, quick in your head. You're like, I can't multiply 29 times 29 in my head. Get out of here. Yeah, you didn't need to, right? All right, everybody's still going good? This will pick up here because I think, well, it's not so hard after we've done the first one. Cosine theta. What am I going to write? Can you guys help me? I know it's Monday. So cosine is adjacent over hypotenuse. Great. Which is adjacent is? 2. And the hypotenuse is? Square root 29. Uh-oh, we have the same problem. Well, it's not that big of a problem, Mr. Kulik. We just solved it a minute ago. Everybody feel good with that? Guess we could start boxing these guys up as answers. Okay. Next one is tangent. Tangent is opposite over adjacent. Great. What's opposite? What's adjacent? Anything I got to do to that? Looks good to me. All right. My 3 new ratios now. Cosecant theta. Cosecant theta is the reciprocal of which one? Sine, right? Well, I'm going to just take my answer from sine and flip it then. Everybody cool with that plan? So where do I want to take the answer for sine to do my flipping? I want to take that one. Why do I want to take that one rather than my final answer? Yeah, if I use my final answer, I'd have the square root back on the bottom, and that's a hassle. If I take my initial answer and flip that, the square root's going to be in the top then, and there's no problems. Work smarter, not harder, right, guys? Okay. Secant theta is the reciprocal of cosine. Yep. So hypotenuse over adjacent. But I'm not going to go back to the triangle to look at this because I've already found the value or the answer for cosine. If secant is just the reciprocal, I'm just going to take my answer from cosine and flip it, right? Which answer would I want to use? The 2 over 29. Why would I want to use, or 2 over square root 29, why would I want to use that version? Yeah, I can avoid having that square root on the bottom. And my last one is cotangent, which is the reciprocal for? Is there anything I need to worry about there? No, man. Super easy. Flippy floppy. All done. What do you guys think on that? No big deal, right? We're just using some definitions, filling in some numbers. Pretty light on the math, heavy on the definition. Okay, well that's easy to do, right? Shouldn't have a problem remembering how to do those kinds. Let's look at another example that's marginally more complicated. Okay, so here it says let theta be an acute angle in a right triangle. If sine theta is equal to 1/3, find the values of the 5 other trig functions. First thing I'd want to do is I'd draw a picture, right? What should my picture be of? A right triangle, very good. And what label needs to be in this picture? Got to put theta somewhere, right? Does it matter where I put theta? No, man. Either spot is fine. I'll put it here just because it feels like the most ordinary place to put it. But like, you can draw your right triangle any orientation you want. You can put the theta as any acute angle. It doesn't matter as long as you're doing everything like relative to that theta. It'll all be fine. Everybody's cool? So we got our picture. Now, it also tells us that sine theta is 1/3. How am I going to use that? Yeah, what sides would I label? Opposite and hypotenuse. So the opposite should be 1, and the hypotenuse should be 3. Everybody's cool with that? How would I find that third side, though? Pythagorean theorem. All right. So where do I plug in the 3? Very good. And where do I plug in 1? Either place, it doesn't matter. I'm going to plug it into 1 just for, got to pick some place. And now we're just going to solve for b. Subtracting 1 from both sides. Then we'll square root both sides. Do you remember how to simplify the square root of 8?
2 square root. Yeah, 2 square root.
Okay, you're close. So you have the right idea. What we want to do is we want to break this apart into factors. The factors we want to pull apart or break the 8 apart into are perfect squares. So the perfect square that's also a factor of 8 is 4. So I can think about this as the square root of 4 times the square root of 2. And what's the square root of 4? Just regular old 2. Is everybody cool with how I filled that piece in? How I did that simplifying? Okay. All right. We already got sine, right? That was given to us. So what's cosine theta going to be? Who can tell me?
2 square root 2 over.
Excellent. And that answer looks fine. How about tangent? Very good. Now, do we like that answer? No. We got the radical in the denominator. What should I do to get rid of the square root of 2 in the denominator? You could do that, but what's actually going to be a little bit easier is to just multiply by the radical part. You don't have to do the 2. Now, it's not wrong to do that. You'll just be left with a little bit of reducing to do if you do that. Here, I don't end up with any reducing, which is my preference. I want to point out one thing here on my answer. Notice that I didn't reduce the 2 and the 4, right? Why didn't I do that? Yeah, one of them's under the radical, one of them's not under the radical. I can't reduce things under a radical with things that are not under a radical. Did you guys see that? Okay. Say important algebra thing that you would have talked about ideally in detail last year that you didn't make it to. So I'm just going to kind of point it out as we go on some of these things that are important algebra skills. Everybody's okay? All right. What are the other three that I need to do? Anybody remember one of the three's names? Okay, that's cosecant is CSC, sure. And which one of the three is cosecant the reciprocal of?
Sine.
Sine. So the answer I should write for cosecant should be? 3 over 1. I'm just going to write 3, though. Everybody cool with that? How easy are these guys to do? Let's do secant next. How would I write the answer for secant? Okay, 3 over 2 root 2. We got the same problem that we had in the tangent. So let's rationalize that denominator. And I guess we should make mention of what's going on here. Remember that square root 2 times square root 2 is just 2, right? We did this before with the square root of 29 times the square root of 29 was just 29. So just to, there's a lot of 2's going on there, just to reiterate where everything is coming and going from. Everybody's cool with that? So the square root of 2 in yellow multiplied to get the regular 2 in yellow. And the 2 in green is just the same 2 in green that carries over. Everybody feel okay with that? All right. Tangent theta. I would write 2 square root of 2 over 1. I'm not going to bother with the over 1 part, though. It's not wrong if you put it there, but it's kind of unnecessary, so I'm just going to forget about it. Again, was this really any more complicated than the previous problem? No, you had to draw and label your own triangle. Woo! Tough, Mr. Kulik. Tough. No, it was not. But that's okay. These are good practice, right? Brand new, like cosecant, secant, cotangent, all brand new. So definitely worth doing some practice on it. What if we want to find sine of 30 degrees without using your calculator? Well, what? What should I start by doing? Yeah, let's draw a triangle. So I've drawn a right triangle. What label does this right triangle need? 30 degrees. Where does it need to go? Doesn't really matter, but I'm going to put it down here because that's the smaller of the two angles I drew. Okay, so I have that. What else do I know? Okay, what's the other angle that I'm missing then? 60. Yep, that's right. Because I know there are 180 degrees in a triangle. Everybody's cool with that? Wait a minute. What are the angle measures of this triangle? 30, 60, 90. That rings a bell. Do you remember this from geometry? This was one of the special right triangles. Why were they special? Because we were able to write their side lengths as ratios. So the ratio of side lengths, the short side is x, the medium side is x root 3, and the long side is 2x. Should you remember this? It's nice. It comes up, it's going to come up again in a couple of sections. So if I use this then, now that I have this pretty drawn and labeled picture, sine of 30 degrees should be opposite, which is x over hypotenuse, which is 2x. And what does that reduce down to? 1/2. Everybody okay with that? Right, because the x on top can cancel with the x on bottom. When I cross them out, they just become 1s. So I'm left with 1/2 times 1, or just 1/2. Well, that was pretty easy. The hard part was remembering that 30, 60, 90 triangle from before. As an aside, what was the other special right triangle? Does anybody remember?
45, 45.
Very good. 45, 45, 90 is the other one. And the ratio of side lengths in the 45, 45, 90 triangle, the legs of our triangle were 40, or our x length, and the hypotenuse is x root 2. We all feel okay with these? Again, we'll remind you when these come up again, but they come up, and a lot of the things that we're going to be using in the future are kind of built around these two special right triangles. So I think they certainly help you remember things going forward, and I think are quite helpful if you have them memorized, although it's not absolutely necessary that you do. But I think it helps make other stuff easier to remember, and it helps understand some stuff coming up here quite quickly. All right. What if I say just find sine of 17 degrees? How am I going to do that? Okay, but if I build out that triangle, what are the side lengths going to be? Can I say anything about those side lengths?
Well, can you subtract 3? Oh, side length.
Yep. You can say the other angle measure is 83, sure.
Yeah.
But does that help us with the ratio of the side lengths?
Nope.
No, it does not. Notice there's no special direction here. What do you suppose we're going to do since there's no special direction?
Wait, no, don't we use the other equation that we just solved? So
I'm just going to type in my calculator.
you can do that.
Oh, yeah. So if I'm going to use sine, cosine, tangent on my calculator, the first thing I need to check is that it's in the correct mode. Very good. What mode should my calculator be in, degree or radian? Degree. How did you know it should be in degree mode? because it's 17 degrees on the problem. Very good. So to check the mode, I'm going to press the mode button right next to the blue second command. I'm looking at this third set of options to make sure that degree is highlighted. If it's not highlighted, just use your left and right up and down arrows to move your cursor so that it's on degree, and then press enter to highlight it. Once you've done that, we can exit back to the main screen by pressing second in the mode button. Then I'm just going to type into my calculator sine 17, close the parenthesis, and press enter. So about 292. Okay, Mr. Kulik, easy. Give me another one of these guys to do on my calculator. I can do all of them now. Okay. All right, hot shot. How about this? Secant 78. You look at your calculator, what's the problem? There's not a button for secant. Uh-oh. But what do we remember about the relationship between cosecant, secant, and cotangent? They're all reciprocals of one of sine, cosine, or tangent. So which one was secant the reciprocal of? Cosine. So I can just write this as 1 over cosine of 78. And that I can do on my calculator. So you could do this a number of ways. You could do alpha y equals, and then use the fraction command there, the first one, and write it as 1 over cosine 78. And you get about 4810. Also worth pointing out, you can do the same thing. You could do just 1 divided by cosine 78. That'll give you the same answer. You could write it that way. Or you could even do cosine 78. Make sure you close the parenthesis, and then you can use this x to the negative 1 button. Remember, the exponent negative 1 is the same as a reciprocal. So you could write it that way. All of those give the same thing. What you need to be careful about on that last one is that you don't get lazy and forget to close your parenthesis. Because if you do that, what you've actually done here is the cosine of 1 over 78, not 1 over the cosine 78. Those two things are very different. But any of those things would be fine. Matt? Absolutely. You guys feel reasonably comfortable on your calc? Okay. All right. One more example in this section. We'll head to the next one. Okay. The directions here say solve the triangle, and they give us this picture. What is the direction solve the triangle asking us to do? That's code for all the sides and all the angles. Very good. All right. Does it matter what order we do things? Not really. What do you want to find first then?
Angle measure.
Okay. So we're missing this angle measure. I'll call that x. How do I find x? You don't have to tell me the answer. You can just tell me what you're going to do. Okay. So we'll do 180 minus 41 minus 90. Right? Everybody cool with that? So there's our answer for x. Just as an aside here, this is the same thing as just doing 90 minus the other acute angle. That's the corollary to the triangle sum theorem, I believe is the name your geometry textbook gives that. It's doing the same thing. Whatever, though. What you said works. What do we want to find next? The other leg or the hypotenuse?
Other leg.
Okay, I'm going to call that one y then. What are we going to use to find y?
Opposites.
So relative to the 41, Bella says y is opposite. Which other side do we know? Adjacent. So let's use tangent. So we'll write tan of 41 equals opposite over adjacent. All I need to do is solve for y. To solve for y, I'm going to multiply both sides by 12 to get the y by itself. So I have 12 times tan 41. Now it's calculator time. So I get about 10.43 for that answer. We feel okay with that? Okay. Well, the last piece then to find is that hypotenuse. I'm going to call that z. What do you want to do to find z? Okay, so relative to the 41-degree angle, Matt's saying that we can do opposite, over hypotenuse. That'd be fine, but that's not the most accurate way we could find that. Why would that not be the most accurate way of doing that? I think, Elise, did you suggest doing opposite or adjacent over hypotenuse? Is that what you whispered? Yeah, why would that be slightly better? What's that say? What's that, Ava? Yeah, so it's not just that it's a whole number instead of a decimal. This was a rounded answer. That had no rounding to it. That was given. Now, for your purposes, when you're taking a test or whatever, it's not going to make any difference. But if you're working for NASA and you're trying to land a rocket ship on the moon, the little bit of, the 10th decimal place that might be a little off, depending on where you did your rounding, could be the difference between your rocket landing on the moon and missing the moon completely. So it does matter, but not to you guys so much. But I do want to just take a moment and explain that there is a better way of doing this, although either way is perfectly fine. So Matt, what you had suggested would work, no problem. So again, I'm going to solve just one of the two. Multiply both sides by z to get rid of the fraction. And then remember, cosine 41 is just a number. So I can divide both sides by cosine 41. And then it's just calculator time. Oops. So I'm going to I thought I hit that. Dog nabbit. All right. Just close this in a minute when it takes a half an hour to load this thing up. So that gives me about 15.90. What do you guys think? No biggie? Very similar to the geometry practice we did at the beginning of the year on the delta math, right? Should feel very, very similar. That's because it's the same stuff. It's not just similar. Okay. So that's where we had left off with sine, cosine, and tangent. But what we want to do is kind of extend these definitions a little bit. So in geometry class, if this angle was like 31 degrees, actually, if you have an angle that looks like this, start here, right? Say we have an angle like this. Again, we're in geometry. We said there's only one way to decide how big this angle is, right? We said that we're always going to look at angles like this. Everybody agree? And we weren't ever going to consider angles that looked like this. Everybody, does that all look familiar from geometry? If I use this convention, though, what's the biggest angle I can draw then? (180 degrees). Very good. Well, if I'm stuck with this kind of convention, the geometric way of kind of thinking about an angle, all the biggest angle I can draw is 180 degrees, right? You know, like I can start here, and maybe I draw one like this, and then I could draw one like, you know, this, and I can draw it like this. But as soon as I draw this way, you know, I have to measure from the other direction. You know what I mean? So 180 is like the biggest angle you can draw in geometry. Let's fix that. So what we're going to do is we're going to define a new way of describing an angle called the standard position for an angle. So let's say that I have this angle here. Okay? I'm going to name one side of my angle the initial side. I'm going to name the other side of my angle the terminal side. And then this point in our angle is called the vertex, right? Where the two arms meet. Everybody's cool? What I'm going to do is I'm going to take the XY axis and I'm going to translate my angle so that the vertex is at the origin. The initial side lies on the positive x-axis, and the terminal side is wherever that lays as a result. And you're like, big whoop, Mr. Kulik, I don't see how this is going to get you any angles bigger than 180 degrees. Well, hold on for a moment. The way we measure this angle now, we're going to define as a counterclockwise rotation from the initial side to the terminal side. So like this then would be my angle measure. Okay, fine. It's still the same thing as you drew before. Yeah, guys, but here's the difference. Don't have to be so sassy about it. And you're like, you're putting words in my mouth, Mr. Kulik. I really don't care that much. Well, here's the difference. What if I draw this angle? As a standard position angle, we've defined this as the angle measure. What do you notice about this angle? It's bigger than 180 degrees. Whoa. Okay. So using this method now, this standard position angle method, what does it appear the biggest angle I can draw is? $360, right? What would a 360-degree angle look like in this method? It'd be one where the initial side was here, and then the terminal side was also here, and we'd have done that, right? Everybody cool with that? So it looks like we can go from 0 to 360. That seem right? We can do more than that. Notice when I've drawn my angles, I've only gone counterclockwise, right? What do you suppose we can do if we're going the opposite direction, if we're going clockwise? Well, those are different angles, right? If I went one direction versus the other direction. So I'm going to refer to counterclockwise rotation as positive angles. Jeepers creepers. And if I go clockwise, I'd have negative angles. So now I can represent angles between negative 360 to 360. Everybody agree with that? Do you think that's all we can do? Nuh-uh! Because when we drew that 360-degree angle, we stopped, right? Just when we got back to the initial side. Is there any reason we really need to do that? Skateboarders and snowboarders in the room. 540. What's a 540? It's like a trick you do. Anybody? So disappointed. Usually somebody has got an answer for me.
Go around once and go halfway again.
1.5 rotations, yeah. So if we want to do a 540-degree angle, we would go around one time, keep going another half a time around, and that would be a 540-degree angle, right? Or a 540-degree rotation. Uh-oh, Mr. Kulik, you're telling me I can spin around this more than once? Yup. So if I have this now that I can go more than one time around, how big of angles can I make? What if I want to do an 800? Could I just keep going? Yeah! And if I can do it counterclockwise, what can I do clockwise? Yes! Oh, well, Mr. Kulik, I guess at the end of things, this really does make a big difference, right? Now I can have a way to describe any angle, whether it's negative infinity all the way to positive infinity. I can do negative angles. I can do angles bigger than 180, bigger than 360, as big as you want. I can draw it now. Ooh, we did a lot there. That's really cool. Do you notice anything between this 540 degree angle and say a 180 degree angle? If I compare those two, what do you guys think? Is there anything that's the same about them? If I look at them, the initial side is in the same spot, and the terminal side is in the same spot. Everybody agree with that? If I just look at the arms of the angle, these are indistinguishable from one another. We're going to give angles like this a special name. We're going to call these coterminal angles. Whoa. So we say that two angles are coterminal if they have different measures, but their initial and terminal sides are in identical locations. That if you stripped off the rotation marks that I've drawn on there, the two would look identical. All right, my dudes, you ready for some examples to practice with a little bit here? All right, let's just start with some drawings. All right. So if I want to draw, say, 110 degrees, let's say draw in standard position. I'll say that's SP is standard position. So if I want to draw a standard position angle, I'm going to start by drawing my XY axes. Whenever I draw a standard position angle, the initial side is always on the positive x-axis. Because this angle is positive, which way am I going to be rotating? Positive angles go counterclockwise, so to the left. How many degrees is each quadrant? 90 degrees, right? Like it's 90 degrees to here. Everybody agree with that? And then like 20 more, I just kind of eyeball, maybe to there. So then I'll draw my arm, and I'll just label that as 110 degrees. That's it. All right. What if I do theta is 372. Okay, well, go ahead and start by drawing here. Put in my initial side. And we start rotating. So 90, 180, 270, 360, and then like 12 more maybe is there. What do you guys think? Is it okay? Do one more. What if theta is negative 258 degrees? So start the same way. Initial side on the positive x-axis. But because this is negative, which way are we turning? Clockwise. So negative 90, negative 180, and then negative 258 will be almost to the end. Do we feel pretty comfortable drawing these pictures? Super important skill to be able to draw a picture correctly. Becomes foundational to much of what we do later on. Seems like, yeah, that's pretty easy. Good, if that's the case. If it's not super easy, try to do a little practice and see if you can figure it out, because it's super important coming up. All right, let's see. Let's do another couple of examples. What if I want to find two angles that are coterminal to 47 degrees? What does coterminal mean again? I think we just said it, right? It means the angles have different measures, but their initial and terminal sides are in the exact same positions. Okay, so maybe I'll try to do this graphically. So here's my 47-degree angle. I'll draw my new angle's initial side. And then to get back to 47, well, I can do one full rotation. That's 360. And then 47 more to get there. So I ended up doing 360 plus 47, or 407 degrees is 360 to it, or is coterminal to it. It's 360 to it. Give me a break, Mr. Gulick. What are you even talking about? Is that okay with everybody? Okay. So there's a coterminal angle. What else could I have done? Well, I did one rotation before I went to 47. Couldn't I have just done two rotations? So there's a second coterminal angle. Do you notice anything, any pattern going on between these numbers 47, 407, and 767? They all end in 7. There's more to it than that. How did I go from 47 to 407? You could add 360, right? And going between 407 to 767, you add 360. Oh, wait a minute, Mr. Kulik. Wait a minute, I see it here. To find another coterminal angle, all I have to do is just keep adding 360, right? Each time you add 360, you're going to get another angle that's coterminal. Is everybody cool with that? What else could you do instead of adding? You could subtract. What's subtracting equivalent to?
What was that?
What's subtracting 360 equivalent to? It's just rotating clockwise instead of counterclockwise, right? Everybody cool with that? Okay, well that's easy, Mr. Kulik. Oh yeah, you think so? What if I give you your angle in radians now? What's going to be the trick here? Think back to section 2.1. I know, that was a long time ago now. In section 2.1, we observed that 180 degrees is equal to pi radians, right? In the previous example, we found to find a coterminal angle, how many degrees did we have to add? Or subtract? 360. So how many radians is the same as 360? 2 pi. Oh, okay, Mr. Kulik. So I just need to keep adding 2 pi, and that'll do it, right? Okay, how do I add pi over 3 plus 2 pi? No, we don't need to use our calculator. I mean, you could. I want an exact answer, though. We could make a common denominator to add the two fractions. What would the common denominator be in this case? 3. So I'm going to just multiply 2 pi by 3 over 3. So 1 pi plus 6 pi is 7 pi over 3. So there's one coterminal angle. To get my next one, what am I going to do? Just add 2 pi again. Remember that adding 2 pi was the same thing as adding 6 pi over 3. We just found that in the previous. So there's two angles that are coterminal. Now, some of you might ask, well, Mr. Kulik, couldn't I have just gotten these exact answers by typing into my calculator? My answer to you is no way, Jose. Your calculator will not write a pi in a fraction because pi is an irrational number. Your calculator lacks the computer algebra system in order to manipulate that. Go ahead. You're, of course. However, what we can do is if we take this initial problem and we stripped the pi's off, we could do that in our calculator to get the fraction and then tack the pi back on. What do I mean? If I do 1/3 instead of pi over 3, and I add 2 instead of 2 pi, and then I press the math and fraction command, that gives me 7/3. If I just tack the pi back onto that fraction, there's my first answer. So kind of the calculator can still give you the exact answer, but you have to remember to take the pi's off and then put them back when you're done. Do you guys kind of see what I'm saying there? Okay. One final example. So what if I ask you, is 85 pi over 6 coterminal to 7 pi over 6? What could we do? Do you want the easy way that's kind of sneaky or the obvious way that's a little bit more tedious? Okay, so the easy way that's kind of sneaky is what I want to do is check to see if the difference between the two angles is that divisible by 2 pi. So if I do that, 85 pi over 6 minus 7 pi over 6 is going to be 78 pi over 6. And I notice that 78 and 6 reduce to be 13 pi. Is 13 pi divisible by 2 pi? No. So are they coterminal? No. Because to go from 7 pi over 6, you would have had to add something other than a 2 pi, right? If you add 2 pi and 2 pi and 2 pi, you can't get to 13 pi. Alternatively, what could you keep doing? You could just take 7 pi over 6 and just keep adding 2 pi until seeing if you could get that one. That's the obvious way to do it that's a little bit more tedious. You know what I mean? Just means a lot of grinding, which is not so bad. Okay. We'll stop here. For next time, you guys should be able to now do up through 44. So I think last time we assigned up to 24. We can now go up to 44. Both of these are going to be on Sunday's problem set.
Honestly.